Let us observe the recoil of a gun when a bullet is fired. The gun and the bullet are in one system. Initially, the gun and the bullet are at rest, which means the momentum of the system is zero. As soon as the bullet is fired, it moves forward with a very high velocity. Thus, there is a force exerted by the gun on the bullet in the forward direction. According to Newton's third law of motion, the bullet too exerts an equal amount of force on the gun in the reverse direction, which is referred to as the recoil of the gun. If Fbg is the force exerted on the bullet by the gun and Fgb is the force exerted on the gun by the bullet, then Fbg is equal to minus Fgb. If delta t is the short amount of time for which Fbg acts, it is the same time during which Fgb acts. From Newton's second law of motion, the product of Fbg and delta t is the change in momentum delta Pb of the bullet. Similarly, the product minus Fgb delta t is equal to the change in momentum delta Pg of the gun. Initially, the gun and the bullet are at rest. Hence, their initial momenta Pig and Pib are zero. This indicates that the total momentum of the gun and the bullet as a system is zero. As the initial momentum of the gun and the bullet is zero, the change in momentum of the bullet and the gun is equal to their final momentum Pfg and Pfb respectively. Thus, the forward momentum of the bullet is numerically equal to the backward momentum of the gun, which is taken as negative. As the two momenta are numerically equal but opposite in sign, their algebraic sum is equal to zero. That is, the total momentum of the system is zero. We started with zero momentum of the system, and its final momentum is also zero. This shows that the total momentum of the system is conserved. That is, it remains unchanged. The law of conservation of momentum states that the total momentum of an isolated system of interacting particles is conserved. System here refers to a conglomeration of particles or bodies. For an isolated system, there are no external forces acting on it. Let us apply this law to the direct collision between two bodies. Let the initial momentum of A before collision be Pa, and the initial momentum of B before collision be Pb. When A and B collide, there are two forces created, one on each body, for the same interval of time delta t. Fab is the force on A by B, and Fba is the force on B by A. These two forces are equal in magnitude but opposite in direction. Now, the final momentum of A after collision is P-A, and the final momentum of B after collision is P-B. Applying Newton's second law of motion to the two bodies, we get Fab delta t is equal to P-A minus Pa, and Fba delta t is equal to P-B minus Pb. Applying Newton's third law of motion, we get Fba is equal to minus Fab. Substituting the values from equations 1 and 2 in equation 3 and resolving, we get PA plus PB is equal to P dash A plus P dash B. This shows that the total momentum before the collision is equal to the total momentum after the collision. This proves that the law of conservation of momentum holds true for all isolated systems. Now let us look at the equilibrium of a particle. When the net external force acting on a particle is zero, the particle is said to be in equilibrium. Applying the Newton's first law of motion to this situation, we can say that the particle is either at rest or in uniform motion. When the particle is at rest, we say that the particle is in static equilibrium. And when the body has uniform motion, we say that the particle is in dynamic equilibrium. Let us check out the equilibrium of a particle with multiple forces acting on it. When two forces act on a particle and keep it in equilibrium, then both forces must be equal in magnitude but opposite in direction. And the two forces must be collinear. That is, the line of action of the two forces must be same. Now let's consider a particle in equilibrium with three forces acting on it. Here, the three forces must be coplanar, that is, they should all lie in one plane. The resultant of any two forces is equal to, but opposite to, the third force. The third force, which is opposite in direction to the resultant and whose magnitude is equal to that of the resultant, is called the equilibrant force. The vector sum of the three forces must be equal to 0. When n number of forces act on a particle and keep it in equilibrium, the vector sum of the n forces must be equal to 0. The vector sum can also be determined making use of the three components of the forces. Sigma F is equal to 0. Sigma Fx is equal to 0. Sigma Fy is equal to 0. Sigma Fz is equal to 0. Common forces in mechanics are gravitational force, which is the weight of a body, contact forces between moving pairs of links in a machine, tension in cables, and tension or compression due to elongation or compression in springs. In this module, we will focus on contact forces. An example of a contact force is the force between a box and the table on which it is placed. The contact force between the box and the surface of the table can be resolved into two components. One along the normal to the surface in contact, and the other parallel to the surface. The component perpendicular to the surface is called normal reaction, and the force parallel to the surface is called friction. Let us conduct a simple experiment to formulate an empirical relationship between normal reaction and frictional force. Place a cuboidal-shaped wooden block weighing 100 Newton on the wooden table top. The weight of the block will be acting vertically downward and will press the tabletop down. The tabletop will press the block up with a force equal to the weight of the block. The upward force of the tabletop on the wooden block is known as normal reaction. Let us now try to slide the wooden block by pulling the spring balance attached to the block. As we slowly pull harder on the spring balance, the friction force automatically increases and becomes equal to the applied pulling force. This automatic increase of the frictional force takes place up to a limit only. The frictional force at this point is known as limiting frictional force. At this point, the applied pulling force is equal to the limiting static frictional force. The block is at the point of impending motion. That is, the block is on the verge of moving but is not actually moving. We can repeat the experiment by placing the wooden block in different positions, such that different surfaces are in contact with the tabletop. We will find that the limiting frictional force is same in all cases. If we repeat the experiment by using a stone and an iron block in place of a wooden block, we will find that the limiting frictional force is different in all cases. Limiting friction increases as the mass of the block increases. We find that the limiting frictional force is independent of the contact area between the two surfaces. When the block actually starts moving, the frictional force experienced by the block is known as the kinetic friction force. The kinetic frictional force is always slightly less than the static limiting frictional force. From the results of this experiment, we can arrive at an empirical relationship between normal reaction and limiting frictional force. These empirical relationships are also known as the laws of friction. They are: static limiting friction is independent of area of contact. Static friction is proportional to normal reaction. It is equal to the product of mu s and n, where mu s is the coefficient of static friction. Kinetic friction is proportional to normal reaction. It is equal to the product of mu k and n, where mu k is the coefficient of kinetic friction. If the force F applied on the block is greater than the friction Fk, then the net force on the block is F minus Fk, and the acceleration A of the block is the ratio of the net force on the block to its mass. If F is equal to Fk, then the net force is 0, and hence the block moves with uniform velocity. If F is less than Fk, then the net force is negative, and it leads to retardation of the block. If we slowly increase the inclination of the surface on which the block is placed, there comes a point where the block starts sliding. At this point, the weight of the block, which is equal to mg, acts vertically downwards. If theta is the inclination of the surface with the horizontal, then mg sin theta acts down the plane and the static friction acts up the plane as shown. Thus, mg sin theta is equal to Fs. The normal reaction on the block acts perpendicular to the surface as shown, and it is equal to mg cos theta. As per the laws of friction, if mu s is the coefficient of static friction, then Fs is the product of mu s and n, which is equal to mu s mg cos theta. As the value of theta increases from minimum, the value of mg sin theta and as well as the value of fs2 increases till the value of theta is equal to a maximum theta max. At this maximum value of theta, the block tends to move down the plane and experiences impending motion. Then the friction is limiting friction. In this case, mg sin theta max is equal to fs max, implies mg sin theta max is equal to mu s mg cos theta max, which gives tan theta max equal to mu s on simplification. Now let us look at a rolling friction. When cylindrical or spherical shaped bodies roll without slipping on a cylindrical or flat surface, the frictional force is minimal. A ball or roller bearing fall in this category. To reduce the friction further, grease or lubricating oil is introduced between the surfaces. Air is used as a lubricant in high precision and high speed equipment. Friction is desirable or undesirable depending on the situation in which it occurs. Friction between the moving parts of a machine is undesirable. We try to reduce friction by using lubrication. Friction is desirable when it occurs between the tires and the road's surface. Because of this friction, the automobile is able to move forward or stop when brakes are applied. We are able to walk only because of the friction between our feet and the ground. We would fall if we try to walk on a slippery surface. Have you ever wondered why a velodrome track is curved? Or, on a rainy day, while driving a car at high speed, what happens if you take a sharp turn on a flat road? You will get the answers to these questions in this module. You have earlier studied the acceleration of a body moving in a circle at uniform speed. Here, Fc, the force directed towards the center of the circular path, is the centripetal force. Centripetal force, Fc, is equal to mv square by r. A simple example of centripetal force is that of a stone tied to a string and rotated in a circle in a horizontal plane. The tension, T, in the string provides the required centripetal force. This tension in the string is due to the pull exerted on the string by the person, which prevents the stone from flying away. Similarly, a car moving along a circular path at uniform speed also requires a centripetal force to keep it moving along the desired circular path. In this module, we will analyze the forces acting on the car during this motion. Let us consider a car moving on a level, curved road. There are three forces acting on the car, namely, weight of the car, mg, normal reaction, N, and frictional force, F. As there is no motion in the vertical direction, the net force in the vertical direction is 0. We can say that normal reaction is equal to the weight of the car, mg. Let us call this equation 1. The static frictional force between the tires and the surface of the road opposes the impending motion of the car in the lateral direction away from the center of the circle. This frictional force, F, is less than or equal to the product of the coefficient of the static friction, mu s, and normal reaction, n. Let us call this equation 2. Substituting equation 1 in equation 2, we get F less than or equal to mu s mg. Let us call this equation 3. The centrifugal force, Fc, is equal to the frictional force F. Let this be equation 4. However, Fc is equal to mv square by r. Where m is the mass of the car, v is the velocity of the car, and r is the radius of curvature. Let us call this equation 5. Substituting equations 3 and 5 in equation 4 and simplifying, we get maximum velocity, Vmax, as the whole root of mu srg. That was about a car moving on a level, curved road. Now let us look at a car moving on a banked road. Let us analyze the forces acting on the car one by one. The weight of the car, mg, acts vertically downward. The normal reaction, N, acts upward perpendicular to the road's surface. The impending motion of the car in the lateral direction is away from the center of curvature in the lateral direction. The frictional force, F, acts opposite to this direction, that is, down the lateral slope. We can resolve the normal reaction, N, into its horizontal component, N sin theta, and vertical component, N cos theta. Similarly, the frictional force, F, can be resolved into its horizontal component, F cos theta, and vertical component, F sin theta. We can represent all the components of all the forces at a point C. Along with the weight mg as shown. As there is no motion of the car in the vertical direction, the net force acting along y direction is equal to 0. Or n cos theta minus mg minus f sin theta is equal to 0. This implies n cos theta is equal to mg plus f sin theta. Let us call this equation 1. We know that frictional force F is the product of mu s and n. Let this be equation 2. Substituting equation 2 in equation 1, we get equation 3 as n cos theta equals mg plus mu s n sin theta. The car experiences acceleration acting towards the center of curvature. This is the centripetal acceleration, and the force required for this acceleration is the centripetal force Fc. Centripetal force Fc is equal to the net force acting along x direction. This gives us equation 4 as n sin theta plus f cos theta equals Fc. Substituting equation 2 in equation 4 and solving, we get equation 5 as n sin theta plus mu s n cos theta equals Fc. But Fc is equal to mv squared divided by r. Substituting this in equation 5, we get equation 6 as shown. From equation 3, n is equal to mg divided by cos theta minus mu s sin theta. Let us call this equation 7. Substituting equation 7 in equation 6 and solving, we get the maximum velocity, Vmax, as shown. Now, dividing all the terms on the right-hand side with cos theta, we get equation 8 as shown. If the frictional force is negligible, the maximum velocity, Vmax, is equal to the whole root of rg tan theta. There is a systematic way to tackle problems in mechanics. Draw a free body diagram. Choose convenient coordinate system. Consider all the forces acting on the body. Resolve the forces in the chosen coordinate system. Apply Newton's laws of motion and solve all the equations to find the unknown variables. Let's take a look at each of the steps involved. To draw a free body diagram, we need to draw a schematic diagram showing all the bodies in an environment along with their links and supports. Then, we consider a convenient part of this diagram, relevant to the problem at hand, as a system. Then, we draw a detailed diagram of this system along with the external forces acting on it. This diagram is known as a free body diagram. This completes step 1 of the solution. In a free body diagram, we do not consider the forces applied by the system on the environment. Next, we choose a convenient coordinate system to resolve the forces involved. Coordinates should be chosen keeping in mind the probable direction of motion of the body. This makes the solution easier. Then, we add details about all the known and given forces on the system, indicating their respective magnitude and direction. Then we resolve all these forces along the chosen coordinate system. Finally, we can take the help of Newton's laws of motion to determine the magnitude and direction of unknown forces. If the problem at hand requires an analysis of multiple systems in an environment, we follow the same procedure for each individual system. To understand these steps, let us take a problem and solve it systematically. Bodies A and B of mass 10 kilograms and 30 kilograms respectively are connected by a rope of negligible mass passing over a frictionless pulley. The coefficient of friction between the masses and the inclined planes is 0.30. Determine acceleration of the system, tension in the rope, velocity of the system at the end of 4 seconds starting from rest. First, we draw the free body diagram. Here, as the two bodies are connected by a rope, we split the problem into 2 parts and tackle them independently. As the mass of B is greater than the mass of A, and the inclination of the plane on which B is resting is greater than the inclination of the plane on which A is resting, B is likely to go down and A is likely to go up the plane. Next, we choose a convenient coordinate system, XY. such that x is parallel to the inclined plane and y is perpendicular to it. We choose x parallel to the plane, as body A is likely to move along the plane. This will make the application of Newton's laws of motion easier. Then, we denote the forces on body A, which are its weight, mg or 98.1 newtons, and tension in the rope T, which is unknown. Next, we resolve the weight of body A along x and y coordinates. The x component is equal to mg sine theta, which is equal to 49.05 newtons. Similarly, the y component is equal to mg cos theta, which is equal to 84.96 newtons. As there is no motion of A in the y direction, we can say the net force along y direction is 0. Summing up the forces acting along y direction and solving this net force equation, we get the normal reaction N as 84.96 newtons. Let us call this equation 1. As A is moving up the plane, the frictional force F acts downward. F is equal to the product of the coefficient of friction, mu, and normal reaction N. Substituting the value of N from equation 1, we get the frictional force F as 25.49 newtons. Let this be equation 2. As A is moving up the plane, we take the inclined plane's upward direction as positive. Using Newton's second law of motion, the net force along x direction is the product of the mass of the body A and its acceleration. Substituting values and solving, we get equation 3 as t minus 74.54 is equal to 10 times the acceleration of body A. Now consider the other part, that is, body B, and draw a free body diagram indicating the forces and a convenient coordinate system. The weight of the body B acts vertically downwards. This force can be resolved into its x and y components as mg cos theta and mg sin theta. Mg cos theta is equal to 147.15 newtons and mg sin theta is equal to 254.87 newtons. As there is no motion of B in the y direction, we can say the net force along y direction is 0. Summing up the forces along y direction and solving, we get the normal reaction N as 147.15 Newton. Let's call this equation 4. As the body B is moving down the plane, the frictional force F acts upward. F is equal to the product of the coefficient of friction, mu, and normal reaction N. Substituting the value of N from equation 4, we get the frictional force F as 44.15 newtons. As the body B is moving down the plane, we take the inclined plane's downward direction as positive. Applying Newton's second law of motion, the net force along x direction is the product of the mass of the body B and its acceleration. Substituting values and solving, we get equation 5 as 210.65 minus t is equal to 30 times the acceleration of B. Since A and B are connected to each other with a rope, the magnitude of their acceleration is equal. Substituting equation 6 in equations 3 and 5, we get t minus 74.54 equals 10a as equation 7 and 210.65 minus t equals 30a as equation 8. Equations 7 and 8 are simultaneous equations with two unknowns, which are t and a. Adding these equations and solving, we get acceleration as 3.4 meters per second squared. Substituting the value of A in equation 7 and simplifying, we get the tension in the rope T as 108.54 newtons. Now, we need to find the velocity at the end of 4 seconds. Given that the initial velocity of the system, v0, is equal to 0, acceleration of the system, A, is 3.4 meters per second squared, and time t is 4 seconds. We can use the equation of motion. V is equal to v0 plus at to determine the velocity at the end of 4 seconds. Substituting the values and simplifying, we get the final velocity, v, as 13.6 meters per second. Another way to solve this problem is that we can combine the two bodies A and B along with the rope into a system. Tensions T acting on body A and B now become internal forces and hence cancel out each other and will not be taken into consideration while writing the net force equation. The net force of the system along x direction is equal to the product of the total mass of the system and its acceleration. Substituting the values and solving, we get the acceleration A as 3.4 meters per second squared. The disadvantage of this method is that the tension in the rope T cannot be found directly. To find T, we have to write the net force equation for A or B, where we substitute the value of acceleration just obtained. That is 3.4 meters per second squared. Let's consider the net force on body A along x direction, which is equal to the product of the mass of body A and its acceleration. Substituting the values and solving, we get the tension in the rope T as 108.54 newtons.